Welcome to Section 2. Now that you understand what an EV is, let's look at how it's built. I want you to picture the EV not as a single product, but as four interconnected engineering systems working together in real time. System number 1. Energy storage. This is the high-voltage battery pack, typically sitting flat on the floor of the vehicle. It stores the energy. It's managed by the Battery Management System, or BMS, which we'll cover in detail in Section 3. System number 2. Power electronics. This is where electrical energy gets converted and controlled. The main components are the inverter, which converts DC battery power to AC that the motor needs, the DC to DC converter, which steps voltage down from 400 volts to 12 volts for your lights, radio, and control systems, and the onboard charger, or OBC, which converts AC power from the wall outlet into DC to charge the battery. System number 3. Propulsion. The electric motor converts electrical energy into mechanical rotation. On most modern EVs, a single-speed reduction gear steps down the motor's high RPM into the right speed and torque for the wheels. And system number 4, control. The Vehicle Control Unit, or VCU, is the brain of the EV. It receives inputs from every sensor on the vehicle: accelerator position, brake pressure, battery state, motor temperature, and makes real-time decisions about power delivery, regenerative braking, and safety. All these systems communicate over the CAN bus, the Controller Area Network, which is the standard automotive communication backbone. Please look at the architecture diagram on your slide. This block diagram is fundamental. Learn it. It will come up in every technical interview in the EV industry.
Let me introduce one of the most important current trends in EV architecture, the shift from 400-volt to 800-volt platforms. Let's go back to basic electrical engineering for a moment. Power equals voltage times current. P equals V times I. Most EVs today use a 400-volt battery system. This is the industry standard: Tesla, Nissan, BMW, Volkswagen. At 400 volts with today's charging technology, you can charge at up to 150 kilowatts. But the Porsche Taycan, launched in 2019, was the first production car to use an 800-volt architecture, and the implications are dramatic. If you doubled the voltage to 800 volts while keeping the same cable and the same current, you get twice the power. Now you can charge at 350 kilowatts. That means the Porsche Taycan can charge from 5 to 80%, but the Porsche Taycan, launched in 2019, was the first production car to use an 800-volt architecture, and the implications are dramatic. If you double the voltage to 800 volts while keeping the same cable and same current, you get twice the power. You can now charge at 350 kilowatts. That means the Porsche Taycan can charge from 5 to 80% in just 22.5 minutes. And because you're doubling voltage while having current for the same power level, the cables can be thinner and lighter. This matters enormously for a car's weight and packaging. Hyundai and Kia took this mainstream with the Ioniq 5 and EV6. Both use 800-volt architecture and support 350 kilowatt charging, giving them best-in-class charging performance in their segment. The industry is now clearly moving toward 800-volt as the next standard. Within 5 years, expect 800-volt systems to be as common as 400-volt is today. Remember this formula: P equals V times I. It will explain a lot of what we discuss throughout this course.